Hello everyone, my name is Eddie Merhej, and today I'll be presenting an introduction to the shape memory alloys, as well as a focus on the copper-based shape memory alloys. For the table of contents, we'll be covering an introduction, the shape memory effect, and its according crystallography. We'll also focus on the copper-based shape memory alloys, their applications, and finish with a conclusion and some references. So, as we all know, society is always pushing to find new ways to advance technologically. More specifically, there's been a recent increase in the need for intelligent structures. What I mean by this is that smart systems with adaptive and intelligent functions and features, and that requires a lot of components such as sensors, actuators, and microcontrollers, which increase both the weight and the volume of those intelligent structures. So there are some alloys with a special shape memory effect that can positively contribute to the design of those structures, and these alloys are called shape memory alloys. These would be the perfect alternative to actuators since they weigh less and take up less volume compared to other components. The shape memory alloys have two distinct mechanical effects, which are one, the pseudoelasticity, also known as superelasticity, which is the ability to recover a large nonlinear strain when loading and unloading the alloy. And number two is the shape memory effect, abbreviated as SME, which is the ability of the alloy to recover its original shape after deformation. And for this presentation, we'll focus on the shape memory effect. So for the shape memory effect, I'll open up the laser pointer here, and we will start at the parent austenite phase at point A over here. And cooling the austenite below a temperature known as the martensite finish temperature will cause the twin martensite phase to form, that is at point B. We have the twin martensite phase. And once a stress exceeding the sigma start level, seen over here, is applied to the twinned martensite, the process of detwinning begins. Keep in mind that the stress level required to achieve the detwinned martensite phase is much lower than the stress required for martensite to plastically yield permanently, which is why they have that shape memory effect to start with. So when the shape memory alloy reaches past the sigma finish stress level, it completes the detwinning process, arriving at point C, which is the detwinned martensite phase. And as the shape memory alloy is elastically unloaded, it keeps the detwinned martensite state and arrives at point D over here. And it's not until the shape memory alloy is heated without any stress applied that the reverse transformation can take place, starting at point E, and the complete original shape recovery to the parent austenite phase that is going back to point A is completed at the austenite finish temperature. And once again, this is only true if there was no generation of permanent plastic strain during the detwinning process. Now, the temperatures at which the shape memory alloy goes from austenite to twin martensite and vice versa, which are over here, are called the transformation temperatures. And keep that in mind because it will come up again in the presentation. Now, to simplify the process, here's another illustration of the shape memory effect. So starting once again at the austenite phase, like we did in the other figure, once it's cooled, it forms the twin martensite. And once that's loaded with the right amount of stress, it forms the detwinned martensite phase. And once again, once it's unloaded and heated enough, it goes back to the parent austenite phase, which is the original shape. Now, without going into too much details and to keep track of time for this presentation, we'll cover some of the crystallography of the shape memory effect process that we just discussed. So the austenite phase can be seen here, and there are different variants within the twinned martensite phase, which are seen over here. And these variants basically self-accommodate themselves in different orientations. And usually there's more than just two variants, but this figure is just simplifying things. So what happens when going from austenite to twin martensite is that shear distortion occurs along the plane called the lattice invariant or invariant plane, also known as the habit plane. And that transformation is called the martensitic transformation. Now there's two different mechanisms that can cause that transformation, and it's either through slip, which is atoms that move one atomic space, or by twinning, which causes atoms to move through a fraction of an atomic space. And then when going from twinned martensite to detwinned martensite, those same variants that we just discussed from the figure basically reorient themselves in a way that they all have the same orientation. Now, when considering the copper-based shape memory alloys, they can be split into three categories: the CuZn, CuAl, and CuSn categories. And these base alloys or binary alloys don't have the best cold workability amongst other limitations and drawbacks. So to be able to improve the alloy's properties, alloying elements are added to them, which is what we see here in this figure, right over here in this section of the figure. We end up either with ternary alloys, meaning a material with three elements, or quaternary alloys, meaning four elements. For example, you can see the letter Y in this figure representing some grain Y seen over here, and that Y represents some grain refining elements, which is self-explanatory. These elements basically refine the grain size. Now, here are some of the ternary alloys along with their advantages and disadvantages. So for the CuZnAl alloy composition, their advantages are that they have great transformation temperatures and they are very ductile, but their drawback is that they have limited operating temperatures and the potential to lose zinc during the melting process, which requires a control of the fabrication process, which adds costs. So for the CuAlNi alloy, their advantages are that they are less susceptible to aging and they have a better microstructure stability. And their drawbacks are that their transformation strain is limited at 3% and they have poor ductility. And finally, the CuAlMn alloy has great cold workability at low aluminum content and these alloys have the best ductility out of these three. But their drawback is that their transformation strain is limited at 2%. And just to make it clear that the composition of each element will have an effect on these advantages and disadvantages, just like we saw here, the great cold workability is achieved once the aluminum in the CuAlMn alloy is very low. And these three examples are just certain examples. There are several others out there. Now, for the quaternary alloys, here are some of their advantages that this fourth element that is added brings over its ternary base alloys. So for the CuAlNi, when manganese is added, it improves its ductility. And for the CuAlMn, when cerium is added, it increases its mechanical strength, ductility, and damping capacity. It should be noted that this is not an exhaustive list of quaternary alloys, nor in the last slide for the ternary alloys, and there are so many of them out there that exist, and others that are currently being studied. You can refer to the report associated with this presentation for a longer list of these type of alloys with their advantages and drawbacks. For the applications, the shape memory alloys are used in a variety of industries for several applications, and we will cover some of them that use copper-based shape memory alloys, such as the CuAlMn shape memory alloy, which is used in the biomedical field in the form of a plate-shaped small device that you see in the figure. And that device measures a couple centimeters long, and it's used to relieve ingrown nails using that shape memory effect. The advantage of this treatment is that it can be done without the need for local anesthesia and could even be done at home by the patients themselves. Another example of that same alloy in the biomedical application is its use in medical guide wires as seen in the figure on the left. It has a resin coat and the tip of its guide wire is angled for better maneuverability when used in branched blood vessels. It allows for great flexibility and can withstand high forces being applied on it, which is needed for this type of biomedical work. This shape memory alloy is also easy to fabricate in the shape of tubes and thin foils, as seen in the figure on the right. And these tubes are not limited to the medical industry, but can be used in several other practical applications where thin tubes are needed. Other applications where the CuAlMn alloy is used include the architecture and civil engineering fields, and its vibration and noise attenuation properties allows it to be applied in the seismic applications, such as energy absorbers in bridges. And for the CuAlBe alloy, it can be used in cryogenic applications, which basically means applications with extremely cold temperatures. It's also corrosion resistant, so that means it can be used and it can be beneficial for marine applications. And it can even be used in dampers for seismic applications. To conclude, an overview of the shape memory alloys was covered for the shape memory effect and the crystallography involved. We also covered the breakdown of the different copper-based shape memory alloys and discussed some of their advantages and drawbacks. And we also saw some of these shape memory alloys are used in existing applications. These are the references. Thank you for listening.